All right, people, this will round out our study of exponential functions here, but it is a good one and practical for possibly your real life. So today we'll talk about modeling with exponential functions. All these exponential functions we see model two kinds of behavior, a growth or a decay, right? And so today, that growth or decay typically depends on the base, right? It depends on if the base is bigger than 1 or between 0 and 1. Well, there's another way to kind of turn it on its head and think about it. Instead of worrying about changing bases or having different bases for different problems, today we're going to just pick the base E for every problem that we have. And then we're going to discuss using that one base. We won't always have growth. We will allow to be having decay if we have a number up here, which is negative. So this model here is really a function. I'd really like to write it as big A of t. That would be new amount at time t equals to what they call the initial amount. They write A0 times the exponential function, e to the k times t. So t is time in this context. And this number k is what's called the growth rate or decay rate, okay? So if that growth rate, if k is positive, we'll have a growth. If k is negative, we will have decay. All right. And so in this context, then we can say that the new amount a is an exponential function of t that's rescaled by the initial amount. So let's do this first example. That's a population type example. I think we've seen one very similar to this when we first met exponential functions. Now we'll just rephrase everything in terms of base E, because we'll just prefer to have sort of one base in our life for exponential functions and exponential models. So this example says a small city had 5,000 people in 2005 and 6,200 people in 2010. So they ask us to create the exponential model. So let's do that. So t will be years since 2005, since the first bit of data they gave us is about the year 2005. So t equals to 0 corresponds to the year 2005. And that means then that the initial amount, a sub 0, which is really stands for the function of t evaluated at t equals 0, will give us 5,000, okay? And notice how this equation is valid if we start to set this up here. If we put in t equals 0 to this model, then we'd get 5,000 times e to the 0. But e to the 0 is 1, so we would get just 5,000 now. Okay, so at this point, this is what our model will be following the sort of procedure above, or the, I guess, prescription above. But now we need to find what is this growth rate, k, right? So we'll use this extra piece of data that they gave us, namely that in 2010, there were 6,200 people in this city. So that is when t equals 5, right? 5 years after 2005. So I'll input this data that year t equals 5, we had 6,200 people following the model that our initial amount was 5,000. So now we have an exponential equation, right? 6,200 equals 5,000 times e to the 5k. But we were just solving those in the last section. And how do we solve this? We'll isolate the exponential function part and then go from there to solve for k. So I'll divide first by 5,000 and get 6,200 divided by 5,000 on the left, and that simplifies to just 1.24 if you like. And that should equal to e to the 5k. Now I have an exponential function on this side, so I'd like to undo it by taking natural log, that is log base e of both sides. So we'll take natural log of 1.24 on the left, and then the natural log on the right will undo the exponentiation and leave us with just the exponent 5k. And now we can just divide by 5 on both sides and get that k equals to natural log of 1.24 divided by 5. Or if you like to simplify, that's maybe 0.043. Okay, I'll say I wrote this answer here that the exponential model can then be a of t equals to 5,000 times e to the 0.043t. But what over here, I wrote a note to myself and to y'all that says, watch out about rounding, though, right? So you might actually prefer to keep this ugly number up there. For the sake of space, I just wrote this abbreviated decimal, but in your actual computations, like say you're on Connect Math or something like that, you might prefer to actually keep this unrounded number up here because it could greatly change your answer to a sort of further question, like say part B. So let's watch that go in action here. So they ask us to predict the number of people in the city in 2030. And so the year 2030 is 25 years after 2005, so it corresponds to t equals 25. Well, now that we have our model, we'll just plug in t equals 25 to that and take to our Texas Instrument and compute away. And so what do we get then? When we plug in 25 to our rounded model, where k was rounded, we get the number of 14,650 people. On the other hand, if we use the unrounded model, we get something like 14,658 people. Now, I know this difference seems kind of negligible when we're talking about a population of this size, but just note that this one is the slightly more accurate answer given the data that we had to make an exponential model. So if Connect Math was asking you to round to even the tens of people, you'd be off because this number would round up and that one would round down. So, so do watch out for that, the rounding issues. Okay, and then we have just one more example in this section, kind of a short section here. So we have a scientist who had 30 milligrams of some stuff, and after 4 hours, that stuff had decayed to just 25 milligrams of some stuff. So our initial amount is A0 is 30 milligrams. And so we'll find the exponential model here. So we know that we should be expecting A of t to equal to the initial amount 30 times e to the kt, where k is the decay rate now. And we'll see that in contrast to the previous example where k was a positive number, this k will be a negative number. So the only other bit of data that we know is after t equals 4 hours, the substance had decayed and the amount left was just 25. So we know that if we plug in using what we have for the model so far, then 30 times e to the k times 4 will equal to 25, which means 30 times e to the 4k equals 25. Okay, and once again, this is just a matter of solving this exponential equation here for k. So we'll divide both sides by 30, and we'll be left with natural log of 25 over 30 on the right side of the equation. And the natural log on the left will undo the exponentiation and leave us with just 4k. Okay. And then we divide both sides by 4, and we're left with k equals to 1/4 times natural log of 25 over 30. If we wanted, we could really write this as another fraction. Perhaps I'll get the marker out here. We could also write this as natural log of 25 minus natural log of 30 divided by 4, if you like. This is just using the property of logarithms. I think it was property 6 maybe from section 4.4, where we take this logarithm of a fraction and turn it into a difference. And now you can see here, natural log of 25 is smaller than natural log of 30. So this difference is a negative number. And in fact, now our decay rate, k, is a negative number. Okay, so that'll do it for that. So then we have our model here. is a of t equals to 30 times e to the 1/4 times natural log of 25 over 30 t. Okay. And so then in the next part, they ask us, how long will it take for this substance to be reduced to 4 milligrams? This is now another exponential equation to solve. So namely, when is a of t equal to 4? So we've set up the equation here. We have 30 times e to the 1/4 natural log of 25 over 30 times t equals to 4. And for a bonus homework, you guys can solve this guy for the time t. But I'd recommend using this unrounded version, even though it's kind of unpleasant. All right, well, that concludes this talk for today. So we will see you next time, where we'll talk about systems of linear equations. Maybe take it a little bit easy after all of this exponential and logarithmic nonsense. All right, well, we'll see you.